When looking at standard position trig, there are some key ideas that we have to think about. So first of all, the radiant angles measure arc lengths around the circumference of a unit circle. So the radian is actually a more natural measurement of angle. It measures length. Position of an angle is very important. So where it's located is very important. So it's called standard position for a reason. The position or where the location of the angle is very important. The unit circle is very useful because it allows us to use the sine, cos, and tan ratios as lengths. So when we talk about the radian in the unit circle, it gives us length along the arc. The sine, cos, and tan ratios gives us length along the x and y. So sine gives you length along the y, cos gives you length along the x, and more importantly, not just length, but position. So standard position are functions, and they are also standard position is related to functions and identities. All three things are related to each other. Okay, so we want to make as many connections as we can. So the first example here, so we're given an angle in standard position is defined by the coordinate -3, +2. So first thing is I want to locate that position. So the position of that coordinate is going to be -3 to the left, 2 up, maybe somewhere around here. Okay, it's good to recognize that it is on below that 45-degree angle line. Okay, so there's my position. It's in quadrant 2. I'm going to draw my terminal arm, and there's my angle theta. Okay, so I'm going to write in the lengths to -3, and then using Pythagoras, I'm going to work out the length of the radius or hypotenuse. It ends up being √13. So once I have this diagram, to work out the sine ratio, the sine ratio is going to be the vertical position, is 2 over square root 13. The cosine ratio is going to be the horizontal positioning, so -3 over √13, and the tan ratio is the slope. So rise over run. Okay, and I can put that negative at the bottom, or I can keep it at the top. It doesn't really, or put it at the side, it doesn't really matter. Now to find the standard position angle, I need to use an inverse. So I'm going to need to either inverse the sine, the cosine, or the tan. Okay, so for this particular purpose, I'm going to use sine. So cosine actually would have been the better one because it's going to actually get it to read directly. But starting with this expression, I'm going to inverse it. So I'm going to say that the angle theta is equal to the arc sine of the ratio +2 over √13. And here I need a calculator. So my calculator is going to do the inverse operation here. So I'm going to apply the inverse, 2 over √13, the arc sine of that, and I get 0.588. Okay, so 0.5880, so I'm just going to round that to 0.59. So theta is equal to 0.59 radians. Okay, now 0.59 radians is in the wrong quadrant. Okay, 0.59 is going to be in quadrant 1. That's a quadrant 1 angle. So I need to then use the symmetry to get theta 2. So there's a formula for this. It's going to be pi minus theta 1. But we could also think of it as this angle that we found, 0.59, is actually going to be this position here, 0.59. That's our quadrant 1 angle. The quadrant 2 angle is just going to be going backwards the same amount from pi. And that's where our formula comes from. So if I do pi minus theta 1, I end up with 2.55 radians. So 2.55 radians is in the right quadrant. So theta 2 happens to be the answer that I'm looking for. So this quadrant, the quadrant 2 angle, is what I want, and that's the angle that I'm looking for. So that's my answer. So here I have an angle. You're given the angle of 3 radians, and it defines a point on the circle of radius 2.4. So first of all, I need to locate that angle. So I know the angle here is pi. This is going to be pi over 2, which is approximately 1.57. So 3 radians is going to be just shy of pi. So I'm going to draw it right there. So that's 3 radians. It defines this point, and the radius of this circle is going to be 2.4. Okay, and this position has a vertical component and it has a horizontal component to this. Okay, so I want to find the x position and I want to find the y position of this particular angle. Now, I could start like this. So I could start and say that sine is the y position divided by the radius. So that's going to give me the sine of the angle 3. And I can do the sine of angle 3 from my calculator, and that would then allow me to calculate y is equal to 2.4 sine of angle 3. Now, the other way we can think of this is sine of angle 3 of 3 radians gives me the y position on the unit circle. And since this is not a unit circle and radius 2.4, I can scale the measurement by 2.4. And this calculation then shows the same thing. So in the end, the y position, if I put this into my calculator, okay, because sine of 3 is we need a calculator to do that. The y position is going to be 3.3386, so I'm going to round that to 0.334. So y is equal to 0.34. Okay, so that's the y position of that angle. The x position can be found. We can start with the ratio again. The cosine ratio is going to be x over 2.4. And that's going to be the cosine of the angle 3 radians. And again, I could rearrange just like I did in the previous one. So the x position is equal to 2.4 times the cosine of 3 radians. Now again, if I recognize that cosine of 3 radians is the x position on the unit circle, I can scale that position by 2.4 to get the x position in the bigger circle. So I still need my calculator for cosine of 3 radians, and calculating that I get negative 2.375, so I'm going to round that to 2.38. So x is equal to, the x position is negative 2.38. Okay, and that looks about right because it's going to be very close to the 180-degree point, which is going to be at 2.4 for x and 0 for y. So I'm just a little bit above the x-axis, and I'm very close to the edge of that circle.